Okay, well, good morning. Yeah, just having a little technical difficulties. Hopefully things go well today. We'll see. Nevertheless, let's take a look at what's going on and get to our browser. And as you guys know, you had a test yesterday. And if you go down here, of course, we have the take home portion. Okay, so the take home portion is here. And part of it was or is from your study guide, right? So some of these questions are from the study guide, some are not. So what I have here for you guys is a take-home portion for test 3, and this is going to be due Monday. So let's take a look at the date of Monday. It's going to be due Monday, looks like May 11th, and this is when you guys want to turn that in. Now, it's going to be in the assignment portion. So to let you guys know, you need to turn this into the assignment portion, and I'm going to give you a deadline. So I'll post it in Canvas, give you an announcement. It's going to be in the assignment portion. You will have a deadline, which means you got to meet your deadline, meaning you got to upload your completed assignment to that appropriate place, right? You scan, PDF it, and that's the deadline. So I just want to let you guys know it'll be due Monday 11th before class. And if it's locked on you and you say, hey, it's locked, it's because you didn't turn it in time. So I'm going to set the deadline there. It's going to lock. You don't turn it in when you please. You turn it in when it's due. And that's what's going on here. So again, that's the take home portion. So anyway, wanted to remind you guys of that. And then if we go to the online transition here, let's get rid of that. Okay. We're going to the calculus of polar curves. And so we're going to start talking about this worksheet that's online called the Calculus of Polar Curves. So that's what's happening today. Also, probably for some people, you may need to review some Trig. Okay, remember, Trig is an important course. If you go to the 241 website with worksheets and videos, maybe I should put that link there too. I mean, I'll put that link in Canvas here. I'll put this link here, up here. In Canvas, I have solving trig equations, and that's a big deal. Okay, we solve trig equations in trigonometry, fundamental definitions there. So you guys will need to know those kind of things. So here's trig equation video that I did. Okay, that you guys are probably going to need to review. And so it's a good idea to review that. Just solving different trig equations. I have 1, 2, 3, 4. I got 4 videos on that, just like I had the introduction to polar curve video. So I do have information there for you, and I guess I'll put that link in Canvas. Okay, so that's going to be important for us. Anyway, that's what's going on, so we know what's going on here. And we're going to do the calculus of polar curves. So in order to do that, let's hope everything works. And let's see, source. There we go. Okay. So, yeah, we're going to go look at the Word here. We need a Word document. There we are. Okay, good. So we have this calculus of polar curves here, and we want to find the tangent line. You remember this thing here? Tangent line, altangent. We want to find this tangent line to the polar curve, r equals f of theta. We just want to consider the following parametric equations to allow for this parameter. So, okay. Let's see what's happening there. All right, let's see what's going on here. So, now we're going to have a polar curve for us. R is f of theta. We've seen those curved last time. And we just want to consider the following parametric equations and allow for the parameter to be theta. So let's see if we can get this pen to work. All right, we'll get out of this. Say, pen, do you work? So we have to ask the pen. All right, this pen is having trouble. All right. There we go. It should be okay now. Okay. Yeah, weird. So here's essentially what they're doing, so you guys know. You already know about parametric equations. This is what they're saying. You have, this was t for you guys last time. X is r cosine t, and y is r sine t. Now we're just going to change that parameter. It's no longer going to be t, it's going to be theta. So this is why you see the equation x equals r cosine theta and y equals r sine theta. Keep in mind, r is some function of theta. We have it here. So we're going to try to find this altangent, right? We need dy dx now again. So the whole idea is to get dy dx. And this is what I've used to derive this. Dy dx we know is dy dt, dx dt. But we change the parameter now to be not t, but theta. So there it is. So you have this theta here for you guys. Now I replace the variable y. Okay, so here's my y. I replace it with r sine theta, and I replace the variable x with r cosine theta. Now, r is a function of theta here. This is my point here. So we're going to have to use product rule when we differentiate. And so this is what we get here by product rule. So I'll write that down. We used product rule here. And this is the formula here for our derivative now. This is what we're going to be using. dr d theta is sine theta plus r cosine theta, and dr d theta cosine theta minus r sine theta. So this is going to be our new formula, ladies and gentlemen, and it's a pretty big formula here. So it's pretty heavy. Okay, so let's go back here to the notes, and let's see how to use this formula. I'm just going to go to 262 here, and we're going to look at the, all right. Okay, so let's write this down for us. And this is what we'll use today. That dy dx will be dr d theta now, sine theta plus r cosine theta, everything over dr d theta cosine theta minus r sine theta. Now here's what you're always going to use. R is going to be that function of theta here. So this is what they're going to give us here. So for every one of these questions here, to find a derivative, they want us to get this r as a function of theta, where this is I'm going to put in red. This is what we'll use. And dr d theta, by the way, is also thought of as r prime. So you can see in a lot of books, as kind of a shortcut for finding dy dx, you'll see r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. So either format is fine. And let's give you guys some notes here, some very important notes here. Vertical tangents here. Let's go back to calculus here. And horizontal tangent. We're going to do both horizontal and vertical tangent. So remember, you'll have a horizontal tangent when the derivative equals 0. But the derivative here has a numerator over a denominator. What that really means is you'll have a horizontal tangent simply when that dr d theta here, sine theta plus r cosine theta, this has to equal 0. But the bottom can't be 0, meaning r prime cosine theta minus r sine theta, this portion down here is not 0. Okay, so you have this definition, and then you say, well, what about the vertical tangents? You guys know about vertical tangents here. It's the opposite. That's when that derivative dy dx does not exist, right? Or is undefined. And that's when the denominator is 0. So you can say, is that when dr d theta cosine theta minus r sine theta is 0? And the answer is yes. So this is what we're going to use. And in our notes, I did mention that. If we can find that, there we go. It's essentially in parametric form. I did say horizontal tangent right here is when dy d theta is 0, but dx d theta, the denominator, can't be 0. So that's what I just mentioned. And similarly, for vertical tangents, points in the curve in which dx d theta is 0, the denominator is 0, but your numerator is not. And certainly, tangent line at a pole. Remember, the definition of a pole here was r theta here. Or it's not. This is a point. When the radius is 0 and theta is arbitrary, any theta, you're talking about a pole. Now, what that does, if you plug in r as 0 here, essentially you zero out this, and you're just left with and you have cancellation here, right? dr d theta then. You just have sine over cosine, which is tangent. So tangent line at the pole, we have this nice equation. So if you're trying to find a tangent when the curve goes through the origin, right? Tangent line at the pole, at least that's the slope, you can find it this way. And of course, dr d theta can't be 0. All right, well, this is setting the table for derivatives here. I'm going to have you guys I'm not going to talk about the area, I don't believe today. We may, but I'm going to talk about another thing we want to look at. So arc length. So let's talk about the arc length formula here. Okay. Remember, you need dx dt, dy dt. But we're not calling it dt, we're calling it d theta. So I need to have a dx d theta, and I need a dy d theta. So we're taking the original arc length formula. Dx d theta by definition is going to be what we just talked about. And dy d theta by definition is what you have here. So when we take those derivatives in general and we square them and add them, this is what happens. This is what you'll see in terms of the algebra. That dx d theta was originally the definition of dx d theta squared. And again, this is going to happen by FOIL. Right? We FOIL this, and this is what we end up with over here. So we do the same thing for dy d theta. We use FOIL. We end up with that formula. Now, what's going to happen is you got this minus and plus, so the middle term is going to cancel, and you're just left with the, for that trinomial, the outer terms here. So now you get dx squared d theta plus dy squared d theta. When we do the arithmetic, meaning we add, what you'll see is we can factor out here a cosine squared. Where is this? We're gonna factor. Where is that here? Yeah, you're gonna add these two terms. Let's add these two terms, and you actually factor out dr squared d theta. And you get 1. Same thing here. You're going to add these two terms, r squared sine squared, r squared cosine squared, and you factor out r squared, and you get essentially you're using the identity that sine squared theta plus cosine squared theta in both cases is 1. And this is where we get the famous dx d theta squared plus dy d theta squared equals dr squared d theta plus r squared. This is going to go under the radical. So that's under your radical. And then now that that's under the radical, we could now integrate. So arc length here very often is written in some books as this is your alpha and beta, square root. They like to put r squared first. But here's the proof, really. They'll put r squared plus r prime parentheses squared d theta, as you guys can see. So I'm going to put that for arc length here. Let's write this down in our notes here. The proof I gave you is just what you guys see. So you can actually, in your own time, if you said, I want to go over that, well, it's in every calculus book you ever read in your life. And it's in these notes. So here's how we find arc length. So as you can see, finding the derivative is going to be important here because that r prime is dr d theta. So like I said, every problem that they give you is based on this function here. And the formulas I just went over, I proved for you, and I wrote this down in your notes. So you might want to take a look at it. So now it's, again, application time. So we get to look at some examples here. Okay, so first kind of example, we're going to do a classic kind of determine Oh, what? You're going to find dy dx at a particular point. So I'm looking at your book here. Let's take a look. So they're going to say things like this. Find the slope of the line tangent to the curve at some value theta. So that's kind of this is what they want us to look at, right? So give you the first example with this. We have to define the curve, right? R here, let's say, is 2 minus sine theta, and theta here is going to be pi over 3. And maybe we should try, let's see if we go to browser and let's go to our famous website just to kind of show you guys what that might look like, right? What kind of curve we're talking about. R equals 2 minus sine theta, and that's not a circle. Okay, so it's kind of interesting here. This is the curve they're looking at, and we're trying to find, and theta being pi over 3, don't forget pi over 3 is like 60 degrees, so it's kind of up in quadrant 1 there. They want to find the derivative, find the slope of the line tangent to the curve for theta here. So it's kind of nice to look at. All right, so let's go back to the iPad, and let's remember here that what they give us here is that function of theta. And if we're going to find the slope, we got to use our formula, right? And you say, well, what's the formula for finding a derivative here? Well, here's our formula. dy dx is r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. And that's going to be good for theta at pi over 3. So a very simple kind of question. So dr d theta, we know, differentiate this function with respect to theta. And we get really the derivative of minus sine theta. Derivative of sine is cosine. So that's minus cosine theta. So this is the r prime that they're talking about. So that gets replaced right up here in these positions. And so your dy dx then will become minus cosine theta. And then you say, well, this is times sine theta plus r. And you say, well, what is r here? Well, r is right here. R is 2 minus sine theta. So we can say this is 2 minus sine theta times cosine theta. Everything over r prime minus cosine theta minus r again, which is 2 minus sine theta, and then we have another sine theta here. So let's write that down. So at this point, what you can do again is use some algebra, right? And I'll write it down here. And you might say use algebra 2 to multiply, distribute. Because you can actually simplify this, hopefully. So you have minus cosine theta, sine theta, plus 2 cosine theta minus, I'm going to do this in alphabetical order, cosine theta, sine theta, that's minus cosine theta, sine theta, and then this is going to be a minus 2 sine theta, let's be careful, and that'll be plus, looks like sine squared theta. So double check. Okay, so let's double check here too. We're gonna have, I'm gonna double check all this. Okay. So we have 2 minus sine theta cosine theta plus sine theta minus cosine theta. 2 minus sine theta times a minus sine theta plus, okay, it looks like we're good. I just see a problem here. Just found my own error. This is down here, going to be cosine squared theta. It's minus. Okay. That's where it is. All right. So let's simplify this. We got 2 cosine theta minus 2 cosine theta sine theta. And then that's our numerator. And in the bottom, we have sine squared theta minus cosine squared theta minus 2 sine theta. So this is what we have as well. Now, the question is going to be, we can do a little bit of simplification. Let's write this here. Sine squared theta plus cosine squared theta. I could do a little simplification right here. So just to kind of remind you here, let's go take a look at a few things here. Let's go to the browser and say we're in 241. Now in 241, I give them a cheat sheet, and they do have a cheat sheet where you have some identities. So you guys can use your trig sheet identities as well. And, you know, so you could take a look and say, okay, is there a nice identity that I can use? I kind of see one. And here's what I see here, right? If you go take a look here, right in the middle, I guess it highlights everything. I want you guys to know I can replace this bottom. If you guys can see, if you guys remember that cosine 2 theta is cosine squared minus sine squared. Okay, it's cosine squared minus sine squared. So I'm going to write this down and give you that detail, that cosine 2 theta is cosine squared theta minus sine squared theta. Let's go back to the iPad. This is what I wrote down, which means since, and don't think that this is a plus. It's not a plus. There's a minus. I can replace this with minus cosine 2 theta. And you say, why? Well, change the signs here. And now I have that same identity. So that's a minus cosine 2 theta. Anyway, anything to help us? Because we're going to need that help. So that's a minus cosine 2 theta. Okay. Now, don't forget, we need this when theta is pi over 3 now. So I have to plug in a pi over 3 for theta everywhere. Pi over 3. Pi over 3. That's 2 pi over 3. That's pi over 3. So it will be helpful for us to know, and this is what I mentioned here, that pi over 3, that's 60 degrees. And I don't know about you guys, but back in Calculus 1, or I'm sorry, Calculus 1, yeah, Calculus 1, trig, geometry, this is a special triangle. 1, 2, square root of 3. So if you guys remember those fundamentals to say, oh, cosine 60 degrees, well, the definition of cosine is adjacent over hypotenuse. Sine 60 degrees is opposite over adjacent. These are the values that you guys use here. And this is why I say you may want to go back to some of those videos in Trig that I did, because it actually helps you find some of these values. So cosine is 1/2. So let's go back here. And I'm going to try to find another color. I don't know. So we know this portion here is 1/2. This portion here is 1/2. Sine is square root of 3 over 2. Sine square root of 3 over 2. And this is going to be cosine of 2 pi over 3. So you might want to note cosine of 2 pi over 3. Now you might say, what is 2 pi over 3? What's the angle, right? So you have to determine this. And it's going to be 120 degrees, right? Because if pi over 3 is 60, double that is 120. So if you recall how to find some of these values, 120 again is in quadrant 2. So here's quadrant 1, quadrant 2. So you got 90 and then plus another 30. This is the angle they're talking about, 120, but you need the reference angle. That reference angle is 60 degrees. But all students take calculus. So what that means is cosine really is the same as cosine of 60 degrees. We know what that is. That's 1/2 because of the reference angle. But we know in quadrant 2, only sine's positive, so that's a negative 1/2. Right? Quadrant 2, sine's positive, that means cosine is negative. So that portion's negative 1/2. So this one is going to be a negative 1/2. So we're going to have to put everything here together now. Okay. So maybe we can just go back here and erase some things. That'll be helpful. We're looking at pi over 3. I'm going to get rid of that. We already know we plug in the angle. And here's what we end up with, right? We end up with 2 times 1/2 minus 2 times, I think that was 1/2, right? And that's the square root of 3 over 2. Over minus a minus 1/2 minus 2 times the square root of 3 over 2. Okay, let's see what this gives us here. 1 minus the square root of 3 over 2. Let's double check. And I'm going to say here this is 1/2 minus now the square root of 3. We got a complex fraction. Doing a little bit of algebra here. Okay, so I can do some algebra. Let's see what we can do here. This is 2 times over 2. 2 times over 2. And we're going to end up with 2 minus the square root of 3, everything over 2, divided by 1 minus 2 square root of 3, everything over 2. And so our 2's are going to cancel. So here's the derivative here. dy dx becomes 2 minus the square root of 3 over 1 minus 2 square root of 3. So there you go. There's the derivative, ladies and gentlemen. And as you guys can see, it does take some work. It takes a little bit of algebra. It takes some derivative. It takes you going back to trigonometry. And let's go find that browser. Going back to Trig and understanding how to find angles. And I would say go back to this first one because you're going to see some more of these kind of things. And this is actually about, how long is this? About an hour and 25 minutes. So I really put some time and energy into helping you guys learn how to do things like this. So, yeah, that's your first example. And it's just really finding the equation of the line. Or actually not even the equation of the line. That's just finding the derivative. This is just the derivative. This is the slope. This is m tangent. It's not even the line. They didn't ask you for the line. And that happens when theta is pi over 3, just to recall. So, yes, ladies and gentlemen, that's kind of the work you go to. And then I'll say to you, they can give you another kind of example. They can say to you, determine, and let's use the exact language they use. We're going to find horizontal and vertical tangents. Yeah, let's find a good location for those. Yeah, they say find the points on the curve. That's going to be interesting. This is their language. Find the points on the curve where you have horizontal and vertical tangents. And we'll start with kind of interesting example, maybe. Let's see. We'll start with r equals e theta. Okay, here's a parametric curve here. So notice r is f theta. So let's take a look at what that might look like. If we go to the browser, you say, okay, here you go, browser, r equals e theta. Let's turn that one off. And r equals e raised to the theta power. And they're actually giving us stuff like this. Okay. Well, let's take a look. And theta goes from 0 to 12 pi. So you guys can see here, this is the curve. We may have many vertical and horizontal tangents here. I can see here a vertical tangent. I can see a horizontal tangent. Quadrant 1 has a vertical tangent. Quadrant 2 has a horizontal tangent. Quadrant 3 has a vertical tangent. And if we go forever, ooh, we get, a lot of horizontal and vertical tangents for this curve. Because this curve goes like this forever, ladies and gentlemen. It spirals forever. And that's just for positive theta. I wonder if we do negative theta values. Let's try that. Minus 12 pi. Does it have anything else? Okay, it looks kind of the same. All right. Any difference? Well, we go all the way deep, 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 deep. Okay, well, anyway, theta could be anything, right? Looks like we have duplication of points even. Anyway, all right, let's get out of that and find and use some calculus. So if we go back and remember a few things for horizontal tangents, we need that equation. Horizontal tangents happen when we have the following, right? Dy d theta is 0, so that's my numerator. So horizontal tangents happen when we have dr d theta sine theta plus r cosine theta. This equals 0. So we have to have that equal to 0 for horizontal tangents. What is dr d theta? Well, that's going to be, if I differentiate e theta, I simply get e theta. So we get e theta for dr d theta. And r happens to be the same, e theta. So we got r and we got dr d theta. They're the same function. Because when you differentiate the exponential function, that's what it is. So you get this equation here. E theta sine theta plus e theta cosine theta. This has to equal 0. For a horizontal tangent, factor out your e theta. And of course, you get sine theta plus cosine theta. And that equals 0. Now, you have to know how to solve some equations here. Meaning, we're going to use what's called the zero product rule from algebra, if you guys remember, right? The zero product rule. That means when you multiply two things together, the first thing times the second thing, and they both equal 0, well, that means either is 0 or both. That means e theta is 0 or sine theta plus cosine theta is 0. And I want to remind people that this actually never happens. E theta could never be 0. There's no theta that exists that'll make that exponential a 0 value. However, this does happen. I can subtract cosine from both sides. I'm not sure if I want to do that, but let's see. And I get sine theta is minus cosine theta. And I know sine over cosine is tangent, so I'm now going to divide both sides by. This is solving a trig equation, ladies and gentlemen. So this is why I'm showing you that video again, solving a trig equation. And this is important, which is why I made those videos. So sine over cosine we know is tangent. Tangent is -1. So the videos I did for trig, and I'll keep going back to those kind of things. Say here's browser, here's trig. These videos are really solving trig equations. There's 4 of them. So you have a lot of reference here for yourself to solve trig equations. Like I said, Calculus 2 is really about review. What I show you that's new is 10% only. The rest of it's 90% of what you already had, which is trig and how to solve trig equations and how to find the values of theta here when tangent theta is -1. So we're going to have to know, what is theta? What are the values of theta? Right? Tangent theta is -1. So if you guys remember here, tangent theta is -1. That's kind of a special situation. All students take calculus, right? You guys remember that? All students take calculus. Tangent is negative in quadrant 2 and in quadrant 4. That looks like a 3. So if you guys remember the angles here of these rays, this is a reference angle of pi over 4. This is a reference angle of pi over 4. We need to know these angles. This angle and then the following total angle. So here's what theta is going to be. The quadrant 2 version. You can say 90 plus, or we can say what, pi over 2. It's pi minus pi over 4. So we say pi minus pi over 4 for the first angle. And that's 3 pi over 4. The second angle in quadrant 4 is 2 pi minus pi over 4, which is really 8 pi over 4. So the second angle will be 7 pi over 4. Now, there's different ways we can describe this. However, I want to give you guys some great detail here. Okay, theta is arbitrary. We have no restriction on theta. So because we had no restriction on theta, we're going to have infinitely many solutions here. And once we go that route, this is a special situation because I have one solution here, which is in quadrant 3. Another solution is 180 degrees different over here. So if you guys remember, as you keep rotating either clockwise or counterclockwise, you can very easily write a general solution this way. We can say that theta, take this angle here, the first one, of 3 pi over 4 plus, all we have to do is add pi, another pi, pi, another pi. It doesn't matter what direction. Go in the other direction. Minus pi, minus pi, minus pi, minus pi. This is plus n pi, where n is an integer value. And I like that so much. Here is the deal. All these details are in the trig videos. And the integer, if you guys remember, are numbers that look like this: 0, plus or minus 1, plus or minus 2, forever. So this is how we find really the angle. This is the theta values for where you have horizontal tangents. Now go back here, and then they say, but they want me to find the points. Now, a point in the polar world is r theta. We just got the theta values. The question is, what is r? Well, r is way back here. So I just have to plug in for theta. What was that? 3 pi over 4 plus n pi. So for every theta, which is 3 pi over 4 plus n pi, I have now the radius, which really means as a solution, here's what they're looking for. R theta format. R theta. R E 3/4 pi plus n pi, and the angle is 3/4 pi plus n pi. And this here, again, is for your horizontal tangents. Right? These are the horizontal tangents, HT. And then you say, well, what do I do for the vertical tangents, right? So for the vertical tangents, just remember, you use a formula. And you say, well, what formula was that? Well, that formula for the vertical tangents was that dr d theta now times cosine theta minus r sine theta. This is 0, where both dr d theta was e theta. So that this equation becomes e theta cosine theta minus e theta. Sine theta is 0. And let's go back here. Let's write it a little bit nicer. We can factor out that e theta again. And you have cosine theta minus sine theta equals 0. And by that 0 product rule, you know that that means e theta is 0, but that never happens. Right? We say e theta is 0. Does not happen. But cosine theta minus sine theta equals 0 does. And that just implies here that tangent theta, like we've seen in the past, equals 1. This never happens. And again, the solutions for tangent theta in general equal to 1 is that theta is pi over 4 now, and that'll be plus n pi forever. Because if you went back to the quadrant here, and I know it's written, well, let's kind of do tangent theta being positive 1. That happens in quadrant 1 and quadrant 3, if you guys remember. Right? You go back to the all students take calculus, quadrant 1, 2, 3, and 4. So I know tangent's positive in quadrant 1 and quadrant 3. That angle being 1, or theta, tangent theta is 1, means that theta is pi over 4. That's the reference. Quadrant 1 reference angle is the angle. Anyway, this is how we get these opposite angles. All you need, again, is 1, but because they differ by whether you rotate clockwise or even counterclockwise, doesn't matter. That's 180 degrees. And that's why you say pi over 4 plus n pi, because you just need one of those solutions if they're opposite. That's only if they're opposite, to get the general solution, because there is no restriction. Right? Here's the angle for theta. There was no restriction on theta. So at this point, we can say r theta, at least for the solution, is in the r theta, because they want location, they want points. R is e to the pi over 4 plus n pi, and the theta part is pi over 4 plus n pi. So ladies and gentlemen, this is kind of our first, foray into, I should say, calculus, where we are looking for a derivative, really, but we're looking for horizontal and vertical tangents. And then let me show you here another example about arc length. So you said, well, what about this arc length stuff? Well, let's give you guys an arc length example. We can start with something like this. Maybe we start with r equals theta squared. And let's remember our arc length formula. S is alpha beta square root r squared plus r prime squared d theta. And they're going to have to give us an interval here. Okay? So they're going to give us from 0 to 2 pi. And if we go back to the browser and we say, okay, browser, what does this look like for us? What is this? R is theta squared. So let's turn that one off and say R equals theta to the second power. Okay. We got another very similar situation. And that's 0 to, we want to send 0 to 2 pi, right? So they really want us to find the length along this curve here. This is really exactly in green. How far is that? How long is that, right? That's what they want us to do. So we're going to try to find that distance in green. And of course, you need the derivative. So dr d theta is d theta of theta squared, which is really 2 theta. Now, we have to square r and square that derivative and put it under a radical. So I'm going to write this down, right? We're going to we need r squared plus r prime squared, which is theta squared squared plus 2 theta squared, which gives us theta to the 4th plus 4 theta squared. Okay, now this is under our radical. And you say, can I simplify this? You sure can. Factor out the theta squared. you get theta squared plus 4. And then you say, is this the square root of theta squared, square root of theta squared plus 4? It is. And is this the absolute value of theta, square root, theta squared plus 4? Remember, theta is from 0 to 2 pi, so theta is positive. So this really means I have theta squared plus 4, right? Theta is positive. It's between 0 and 2 pi. That's what they told us. So all we have to do, ladies and gentlemen, is integrate from 0 to 2 pi theta square root theta squared plus 4 d theta, arc length. And now you say, well, how do I integrate? Well, this is a u sub question where u is theta squared plus 4. du d theta is 2 theta, or we can say simply that d theta is du over 2 theta. 0, 2 pi theta, u to the 1/2, du over 2 theta, where they cancel. So I end up with 1/2, 0 to 2 pi, u to the 1/2 du, and that gives me 1/2 u to the 3/2 over 3/2. And I'm going to keep this at the very end, so I'm going to say this is 1/2 times 2/3 u to the 3/2, which is 1/3 u to the 3/2. Now I can do a few things. I can say, I can put this back, right? What is u again? It's theta squared. Well, here's what we can do. Let's look at the limits here, right? This is theta, and this is theta. So since u is theta squared plus 4, when I plug in 0, I get u is 4. So the lower limit here for u is 4. And when I plug in 2 pi, we get u, not mu, u is 4 pi squared plus 4 because I have to square 2 pi. So my upper limit is 4 pi squared plus 4. Let's double check. Yeah. So now I can apply the limits, and that will be 1/3 4 pi squared plus 4 to the 3/2 minus 1/3, really 4 to the 3/2. There's a little bit of algebra I can do here. I can factor out that 4. So I got 1/3 here. And I can say 4 now times pi squared plus 1. That was to the 3/2 minus 1/3 4 to the 3/2, which is 1/3 4 to the 3/2 times pi squared plus 1 to the 3/2 minus that 1/3 4 to the 3/2, and then we can factor out the 1/3 4 to the 3/2, and we're left with really pi squared plus 1 to the 3/2 minus 1. There's some more algebra we can do, but let's double check here. Yeah. Let's double check. It looks like we're okay. I can do a little bit more algebra, but I think I'm going to end there with the algebra if you guys like. Oops. Yeah, that's not what we want. Right? We want a square, a rectangle. Fun, good stuff. Let's double check. Is there, let's see. Yeah. Yeah, there's a little bit that we can do. I mean, if you really said, I want to write this, sometimes they write, you guys know, 4 to the 3/2 is really 1.5. So they'll write this as 1/3 times 4 square root of 4, and that's going to give you 2. and you get pi squared plus 1 times square root pi squared plus 1 minus 1. So you can end up seeing in back of the book, if I change this, square root of 4 is actually 2, right? So you can see something like this in back of the book, that the arc length is really 8/3 pi squared plus 1 square root pi squared plus 1 minus 1. And that would be something that we can also do. So again, a little bit of algebra goes a long ways, and a little bit of trig goes a long ways too. And what you guys are seeing definitely is how to find arc length. Now, again, I'm going to give you guys, let's give you guys some homework to get started on some of this stuff in this section, which is 11.3. And I'm interested in the calculus. So it's going to be, to start today, well, you guys can do like 55 to really, I'll do 55 to 66 all maybe. And, you know, I got in some of these. And of course, I'm going to give you guys some more examples to put online for you. Examples of how to find derivatives, how to find horizontal vertical tangents, and how to find arc length. This is good, fun stuff. So I will give you some more examples. Thank God we got the technology to work today. Everything that I touched did not work. It's crazy. So finally got it up. So good. I'm glad we got this in. Anyway, okay, if you have any questions or issues, you know, come see me in office hours again. And then I'm going to remind you guys, test 3 take-home portion. I don't know if you guys appreciate that. Maybe you do, maybe you don't. But historically, people have. Let's find it. You go, okay, where is that again? And it's due on Monday, right? Monday before class. Before class on Monday. Nope, it's not there. It's going to be, here we go. Test 3 take-home portion. You got about 8 questions. About half of those were probably on that study guide. So if you worked on that study guide, you might even be done with those. The only new questions I gave you is question 3 and question 4, really. And that's a Laplace transform. This is stuff that you guys see in other math courses and other applications. So I might even put up a worksheet eventually on some of those too, because they're amazing. All right. Oh, you guys do appreciate it. Good for you guys. We're going to give you guys that take-home stuff. This is all. And by the way, the reason I do this for you guys is because, you know, like I said, an hour and 10 minutes isn't good to give a calculus test. That's ridiculous. But here's that take-home portion you guys can work on. And it's designed to help you in your future. And that's really what it is. And you might say, well, this is a little longer. Well, yeah, that's the whole idea. Take your time, see how this goes. You know, it'll be due next Monday, but double check. I really like the Laplace transform questions, right? 3 and 4. So you might want to do a little bit of reading. And those are applications that you see in other classes. They're really, really heavy applications. And I might even put a video up on some of those Laplace transforms because it's important. Love those things. And it's an application of improper integrals. So anyway, have a great day. You guys stay safe. And, you know, work hard. Keep your head in the game. And remember, get to your homework as soon as possible. Don't wait till the last second. And yeah, the take-home portion is not worth 20 points. It's 25 points, so I'll fix it. And it's worth 25, not 20. The test in class is 125. So take it easy, you guys. Sorry about the delay, but none of the technology worked. It is scary how everything could not work. That's weird. Take it easy. See you guys tomorrow.